Joey, you may proceed.
Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today, we are here for the 28th lecture under the Centenary Lecture series to be delivered by our honorable alumnus, Shyam Ganguli, on the topic Exciting World of Developing and Utilizing Standards in Real-World Application. The session will be chaired by Professor Kamal Sharkar, who is Associate Professor of Practice, University of Texas, Rio Grande Valley, USA. Over to you, sir.
Kamal,
Chair, may please take over.
I got it. Okay, thank you. I got it. Okay. It is my great pleasure to introduce my friend Shyam, Mr. Shyam Ganguli. We graduated together from B College in 1968 from the same department, Mechanical Engineering. Interestingly, our path diverged, and we didn't have any communication for almost 50 years. Then suddenly, we bumped with each other. Shyam simply blew my mind with his astoundingly challenging professional paths he chose and succeeded. We really bonded again. Let's start backward to show Shyam's resilience, focus, and discipline. Even now, we are way north of 70, still he goes to swimming twice a week, plays tennis twice a week, and other 2 days, no, he doesn't rest. He tone his body by going to the gym. Let's go back now. After graduation, he went and joined Merchant Marine, and within few years, he became the chief engineer. To give an example, he took care of a ship, we are talking 40,000 tons in the vast ocean, and he navigated through typhoons and storms. Still, he was not happy. So he went back to UK, start a second career. And he aced the chartered engineering exam and got awarded for that. Then he joined the UK Ministry of Transportation and Energy to start his next career to plan, review, and approve new ship construction. As a result, he worked on semi-submersible oil rigs in North Sea and South Korea. Being Shyam, he didn't like it either. He changed his course again. He came to the US and started all over again, knowing fully well that he had to start from the bottom. And he did it. And guess what? He went way up to the level of assistant vice president, and he prefers to be called by the other thing. He's an operations chief engineer. He's an engineer by heart, by mind, by thought process. He, along with his another 17 or so engineers, took care of about 2,000 engineers from technical perspective to handle multi-billion-dollar industry called FM Global. For his work, he went to China, Germany, Canada, Brazil. So he did everything in life in terms of occupation, in terms of profession, in terms of challenges. He designed about 20 standards in anechoic chamber, large-scale solar plant, steam turbine. He'll talk about that. Okay, and still he's going strong. Thank you, Shyam, for coming and giving an opportunity for our students to show what a mechanical engineer can do, almost anything. It is left to their imagination. Shyam, now it is your call to start playing. Thank you, Shyam.
Hey, Kamal, thank you. So, Bidut, will you put the presentations on the screen, please?
Yes, Dr. Pradeep Mondal will do. Thank you.
Okay.
Pradeep, please.
Okay. Yeah. Thank you, Kamal. Thank you, Kamal, for that introduction. Even I was impressed. Thank you, Sudeep Ghosh and Dr. Bidut Pal, for making this seminar possible. I appreciate the opportunity. Here on the side, you will see that I have given you my email address. That's because if any of you want to contact me down the road, you have that handy. Every slide has a number on the right-hand top corner here. You can see my screen pointer. And at the end of the seminar, if you have any questions, please quote that number so I know where to go. Next slide, please. When we were going to B college, we did not always understand why we are studying all these subjects. What use will they be in future? The education in B college gave me an unique ability to read, understand engineering documents, specifications, drawings, etc. And also, it helped me and all my batchmates like Komalaku to make a living over the last 50 years of our career as an engineer. So I thank my teachers and my alma mater for my education. Here is a special thank you for Dr. Umitavo Ghosh, who was our teacher between 1963 and 68. Thank you, sir, for everything you did for us. Next slide, please. Is Dr. Ghosh here? And I don't know. Here is my objective. I'm trying to explain the importance of engineering standards in the life of an engineer. Most of you are experienced engineers. Probably don't have to emphasize too much on that. But particularly, I want to show you the pitfalls of not following standards and how things can go wrong in a hurry. To keep matters simple, all the problems have been explained anecdotally and without using any theory E equal to mc square equations. Go to the next slide. Okay, what is an engineering standard? Basically, it's a tool to make sure our project is designed and executed well. Behind every standard, there is years of engineering experience. And that experience is synthesized and concentrated into a single document for the engineer's benefit. Standards don't say what not to do. We have to keep it simple, direct, and straightforward, so we cannot clutter it up with what not to do. It does not explain the recommendations, and that's where engineering education comes handy. Go to the next slide. Okay, there are multiple types of engineering standards. Institute of Electrical Engineers, Mechanical Engineers, Civil Engineers, Structural Engineers, etc. They write institutional standards. These are written by very experienced engineers with years of experience, and you can pretty much take them to the bank. Standards like National Fire Protection Association in the US are written by public committees. There are some problems with that because sometimes to revise them or find errors or get an answer from them is very, very difficult. In the US, Underwriting Laboratory and FM Global, we write standards for our customers. Actually, we are authorized by the federal government to do so, and they also audit us average once every 5 years to make sure we are doing our job correctly. Manufacturers' manuals for large machines like steam turbines, gas turbines, etc., are essentially standards in their own right. But watch out, that every manufacturer write a manual for their own machine. So you cannot use an Alstrom gas turbine with a GE manual. It does not work very well. Next slide, please. Okay, since I spent the last 31 years of my life with the FM Global, I want to give you a background of the FM Global story. There was a Boston textile mill owner, his name was Zachariah Allen, and he had a problem in 1835, which was a recession year. He was not making much money. His mill in Rhode Island was catching fire average once a week. So his fire premium was very high and it was eating into his profit. It was eating his lunch. So he noticed that the cotton fibers deposited on textile machines caught fire very easily. He had a brilliant idea. What if he keeps the textile mill clean? And guess what happened? The frequency of fire occurrence was reduced significantly from once a week to average once a year. So he went to his fire insurance company and said, give me premium rebate. They said, get lost. You pay exactly the same as everybody else. So he came back and called his 10 local mill owners, his friends, and he shared his observation with them. So together they formed a club, which is a mutual insurance company. Everybody put in about $100, which was a ton of money in 1835. And they hired a person to visit every mill regularly to make sure cleanliness was maintained. That was the first field engineer in FM Global. Now you know what FM Global field engineers do. They go to plants and make sure they're clean. But no, that's not the point. Okay, everybody paid a premium, but end of the year, the unused premium is a specific term. It means all expenses, salary of that hired person, and all the losses they have to pay, and the net remaining money they return to the owners as part of their profit. This is the concept of a mutual company, and it was born in 1835. By the way, Zachariah Allen was an engineer and a scientist in his own right, and he invented a whole bunch of other stuff, and that's a big story. He survived for 82 years and was very prosperous. Okay, after 187 years of growth, our premium income now is about $7.8 billion gross. Our asset or surplus is over $20 billion. This is a specific term, surplus. That means this is the financial firepower we have to pay all our losses. It's still a mutual insurance company in the way Zachariah Allen imagined. Profits are still returned to our customers as premium rebates. Worldwide, we have 2,000 engineers and 6,000 employees now. Engineers are hired in their own countries, but they have to come to the US for intensive training so that whether you are an US engineer or Indian engineer or British or German engineer, you work to the same high standards and produce the same high quality of work. The FM Global office in India is in Bangalore. So this is for our newer engineers and soon to be graduate engineers. If you are interested in a career in this field, you can always find them on the Google and contact them directly. Nowadays, our field engineers visit every factory that we insure for risk analysis. When I say risk, it is all risk basis. So they will evaluate fire protection, earthquake protection, structural protection, snow load, rain load, you name it. And these reports are about 50 to 100 pages long. It's very involved process. This is insurance based on engineering analysis. We do not have any actuary working there. In other words, nobody is calculating probability of a loss and basing insurance premium on that. We base our insurance product on this all risk basis. So to do this job, every engineer must have a standard so that all over the world, no matter whether you are in China, India, Europe, you walk to the same standard. You don't invent anything. You evaluate a facility based on FM global standards. Now go to the next slide. Okay, how is FM global standards written? Two basic pillars. One is our research data, which is generated at the FM Global Research Laboratory in Rhode Island, and also our loss experience. Every loss over $1 million is thoroughly analyzed. What happened, what went wrong, and more importantly, was our standard right or wrong? Did the standard fail? And we can update the standard based on that loss experience as quickly as we can. The standard is basically drafted by research engineers and scientists. These are PhD engineers working in our research laboratory and engineers with expertise in specific subject. That's where I come in. These standards are reviewed by all 2000 FM global engineers. Normally, all of them don't do it. We normally get about 100 feedbacks, but they are very constructive. We incorporate all of them, or we have to notify the engineer why we did not take his comment into account, his or her. It's approved by senior management. It is revised as needed or every 5 years. Now, all these standards are given to anybody in the world for free. So you can go Google FM Global Loss Prevention datasheets and download any standard you want for free anytime you want. We do not use public review process like other standards because public don't have the engineering experience to be able to review them. And we also work with standard writing authorities in every country, including India, to influence the authorities to incorporate our standards into their standards. And that's an ongoing process. We have two engineers, right now I think we have two, in Bangalore, whose job is to try to attend as many standard writing meetings as possible to influence them to incorporate our specifications into their standards. Next slide, please. I told you FM Global Research Campus in Rhode Island. This is the research campus. This is in a 500-acre property, and it cost about $130 million to build over the years. Here, we can do full-scale simulation of fire, rainstorm, windstorm, hailstorm, dust explosion, flammable liquid exposure, anything and everything. This is just a small list, not a complete list at all. And there are about 30 or 40 engineers and scientists working there. And our job is to keep in touch with them to make sure that what they are doing and what we are doing are in sync. In other words, if I see a problem in the field and I want to do research, I write a research project for them to work on, and they will return the results sometimes later, which we can bring into our standards. Go to the next slide. Next slide. Okay. This is the large burn laboratory in the FM Global Research Campus. This burn laboratory is, you can see the internal volume is very big. The problem of doing full-scale fire testing in a smaller laboratory is that oxygen depletion takes place as the fire progresses, and also as the sprinkler system or water application rate increases, the humidity reaches 100%. Eventually, you can extinguish any fire with lack of oxygen and high humidity. So what caused the fire to be extinguished? The fire protection system or the lack of oxygen? So that's why we carefully maintain 21% oxygen throughout the test. And also the humidity is maintained around 40%. All tests are instrumented to nth degree. We measure the radiant heat because that can ignite surrounding combustibles. The draft, the convective heat output. If you can see on the top, there is a semicircular thing that's called a cone calorimeter. So the cone calorimeter is connecting all the convective gases, and it is measuring the megawatt output of the fire. So all this data is incorporated into these two standards, datasheet 8. Every standards had two numbers. The first number 8 is the series, which is storage, and it gives you protection of storage of anything in a big warehouse. And datasheet 3-26 is non-storage occupancies, like a semiconductor facility or a office building, whatever. Okay, one word of caution: when you are doing your design, particularly fire protection, if a consultant walks in with a computer model and says that, this is too expensive, so I have done a computer model to come up with a protection criteria for a 40 feet high plastics commodity storage fire, run from him like the plague, because FM Global, with 187 years of experience and a 300% computer science laboratory, have not been able to do this so far. Down the road, they may, but not yet. Okay, go to the next slide, please. So these are the standards that are based on the hydraulics laboratory, and it gives a theoretical background of doing network analysis of hydraulic systems. Fire protection is a hydraulic network analysis problem. So our engineers have to go into every factory and they have to do a network analysis of their fire protection system, make sure it can provide enough water to whatever is burning in the building. That's a complex process. It takes years of experience and a sophisticated computer program to do. And it also gives a lot of responsibility to a young field engineer, because if the fire protection is inadequate, the plant will most likely burn down in the event of a fire, and that will cost FM Global millions and millions of dollars. So this is the bread and butter of the work, but that's not all of it. Go to the next slide, please. Loss data analysis. Remember, we keep track of every loss, and we put that in a database and we analyze that database quite regularly. And the loss data analysis says large steam turbine power plants in thermal power plants are burning down to the ground, costing hundreds of millions of dollars. So what FM Global did, in the large burn laboratory, they made a mock-up of a very large steam turbine generator unit. It was not full scale, but it was large scale. And then we designed fire protection system and ran 35 or 40 tests to see what can prevent that fire from burning the plant down. And based on that research data, this standard is written. This standard was written in the early 2000s, and after that, multiple plants have incorporated our standards into their thermal power plant, and the loss traffic in the protected plants have really gone down. Actually, there is no loss traffic right now. Now, I am not going to go into the details of how to protect a steam turbine generator, but I want to give you the little theory behind this standard. These steam turbines are running at about, this is 3600 RPM. So there is a huge rotational energy stored in the unit. And lubricating oil, let us only talk about the lubricating oil system right now. Lubricating oil goes to lubricate all the bearings at the HP, IP, and LP turbines. And the capacity of the oil can be anywhere between 10,000 to 20,000, 30,000 gallons. It's a huge system. So this turbine system is mounted on a pedestal 30 to 40 feet high above the floor of the unit. And The bearings are at that level, and below the turbine are the hot reheat valve, the medium pressure steam turbine, superheat steam valve, hot reheat valve, etc., the low pressure turbine, and all the associated steam pipelines. Now, the lube oil has an auto ignition temperature of around 600 degrees Fahrenheit. That means if the oil leaking out of the turbine falls on a steam pipe with a surface temperature 600 degrees Fahrenheit or above, it will burst into flame without any source of flaming ignition. So now we set the stage right. This machine, as soon as there is a fire, if we shut the oil down, all the bearings will run out and the rotor will settle down into the stator and make physical contact between the rotor and stator, and that will cause significant damage to the turbine. So this turbine is running at full load. Something went wrong. The master fuel trips. This machine will keep rolling for 40 minutes. Oil will be falling on the hot surfaces, ignite fire, settle down in the condenser pit. It will burn there, and there will be a huge fire. We cannot stop the oil. We cannot extinguish the fire because a three-dimensional fire where the oil is burning as it is falling and then burning up as it is accumulating below the turbine cannot be extinguished by any sprinkler system. So how do we protect the turbine? What we do is we provide a sprinkler protection around this area so that the hot gas is coming out of the fire is below 500 degrees Fahrenheit that touches the turbine casing, and that will not cause any damage to the turbine. That is the basic theory of the system. There are three major oils: hydrogen seal oil and control oil. I want to talk about the hydrogen seal oil a little. This generator is cooled by hydrogen about 40, 50, 60 psi pressure. There are two oil lubricated seals at these two ends so that hydrogen does not leak out and create an explosive atmosphere. And the drain oil comes from there into a hydrogen detraining tank system. And then hydrogen has to be detrained from the lube oil. So we have to put a spray system around the jet fire. So we calculated that a 1/4-inch crack in the pipe can produce about 50 megawatt of energy, and that will heat the soft underbelly of the generator, and the generator insulation will melt. So we can reduce the temperature of that heat to about 500 degrees Fahrenheit to protect the generator. Control oil system is normally very small and less hazardous fluid, does not normally create a problem. Go to the next slide, please. This is a pulverized coal-fired boiler. Some of you are familiar with this thing. So far, we have been pumping forced draft air into the boiler and taking the flue gases out and putting it into the stack with all the atmospheric pollutants going into the atmosphere. Now, most governments are demanding that we put a bunch of pollution control equipment between the flue gas exhaust in the boiler and the stack. This can consist of back-type filters, electrostatic precipitator. This is a desulfurizer. Desulfurizer means coal may contain sulfur, so the sulfur dioxide going into the atmosphere causes acid rain. So you inject a lime slurry into this thing to remove the sulfur dioxide and sulfuric and sulfurous acid. The problem is the forced draft cannot push all those gases through so much resistance newly introduced into the circuit. So you have to put a booster fan here to draw the flue gases through this system and push it out to the stack. This furnace envelope, this is about 8 to 10 story high. It is designed for 15-inch vacuum because when the flame collapses, there is a 15-inch vacuum automatically created in the furnace envelope. So it is designed to withstand that and not become squished or implode. However, in the event of an upset condition, this fan, the suction pressure is way above 15-inch vacuum. So if the full draw of this fan is imposed on the furnace when there is no flame. This furnace will squeeze like a soda can, and that will cost about $30-40 million. The solution to the problem is, in the event of a flame failure, you either slow down the fan, or you close the damper, or you use a bypass. Whatever you do, you just avoid putting this full vacuum onto the boiler. And that's a new hazard not always clearly understood. Go to the next slide, please. Okay, I have given you the data on this slide in my talk, and this is for your records only. Go to the next slide, please. Here is a gas turbine. This is a pretty standard machine, and it is used for driving a generator mostly. These two standards, 7-79 and 13-17, gives all the details you need to protect a plant involving where the prime mover is the gas turbine. But two hazards are often missed, and I'm going to discuss those two hazards only. The first one is, this is the compressor, right? This is about 14 to 18 stages drawing at atmospheric pressure, putting it out at 500 psi and probably 4 to 500 degree Fahrenheit. That air goes into the combustion chamber where natural gas is burned, and it is coming out at about 2200 degree Fahrenheit, hitting the first two stages of the turbine blades. Now think in terms of these blades. They're spinning at 3600 RPM. That is a huge centrifugal stress. And also there is an axial thrust, which is creating a torque on the turbine, and also the 22 degree Fahrenheit gas. Not many metals can withstand this kind of harsh treatment. So what you do from the compressor, here are some pockets. These are called bleed pockets. And you can see there is slight little openings in there. So compressed air leaks into these pockets and accumulates there under pressure. So you tap off the high pressure air and you put it back into the shaft, and through a hole in the shaft, it travels axially towards these blades and then comes out radially to provide cooling for the blades. Go to the next slide, please. Now look at these blades. These blades, you can see it has got a series of holes in the leading edge. It has a series of holes for the surface area and has a series of holes here for the trailing edge. That compressed air is coming out through these holes and creating a thin layer of cold air on the surface of the entire first and second stage blades. So when the 2200 degree Fahrenheit temperature gas hits these blades, they hit that cold air front and not impart their heat directly to the blades. This particular blade has lost the tip of the blade, and the air comes in here and it has broken into pieces. This is about a $30-40 million loss. The reason behind that is, go to the previous slide, please. Okay, the reason behind that is air is taken in through an evaporative cooler. So there are a bunch of filters here, and you inject water into the airstream. The water evaporates, draws its latent heat of evaporation from the air, and comes to the compressor here. But that water has to be very pure. The salt content, dissolved salt content of the water cannot be anything more than a parts per billion level. So it has to be chemically treated water. And we quite often have seen plants are using tap water in this system. So what happens, the excessive salt travels through the turbine and comes out of here. And you saw the ports on the blade that distributes the cold air to the blades and choke up those cold air passages. So the blades overheat and fail. The second problem is that the same, stay on the previous slide for a minute, please. The second problem is the same air, as it comes out of the evaporative cooler, and is sucked in by the first stage blades is speeded up. And that's a refrigeration effect on the air, and the temperature can be substantially less than atmospheric at this point because of the speeding up phenomena. So that water particles can turn into ice and impinge on those blades and cause a severe erosion of the first few stages of compressor plates. Go to the next slide, please. So the bleed air valve, from the one of the bleed air valves feed hot air back into the recirculates it back into the air intake system, and that's called an anti-icing system, which destroys the ice particles. And this system should operate when the ambient temperature is 40 degrees Fahrenheit and the humidity is 40%. And sometimes we have seen plants don't understand the problem, particularly in desert areas, and shut the system down and cause erosion to the compressor plates. The other hazards are very well explained in the standards, and I don't have the time to go there. Go to the next slide, please. Roof-mounted solar photovoltaic systems. And this datasheet contains all the details you need to install them successfully. I want to draw your attention to two different problems. One is the solar panels are mechanically fastened. That means they are attached to the roofing through the roof into the building and fastened with nuts and bolts. That causes penetration of the weather-tight roofing surface. Those penetrations can be sealed. However, owners sometimes don't like this. So what the industry did, they came up with a paver block system. These pavers are concrete blocks. They are on a friction pad and they are not attached to the roof. There is no penetration here. The weight and distribution of the paver blocks will have to be carefully calculated based on the wind uplift forces on the solar panels. All that details is given here. Any engineer can do that. However, look at this. We are adding additional load on the roof. Lot less here, but lot more here. And that causes a roof collapse problem. Go to the next slide, please. So with roof-mounted solar panel system, collapse is an issue. We need to compare the weight of solar panel with the available roof life load. You may need to seek help from a structural engineer or find the structural drawings of the facility to figure out what the roof life load is. Paver blocks avoid roof penetration, but they add a tremendous amount of weight on the roof. And also, paver blocks are not recommended in earthquake-prone areas because every earthquake in a subduction zone in the tectonic plate level has a component of acceleration that is vertical. And as you know, the vertical acceleration will have the effect of lowering the weight of the paver blocks in a shaking situation, and solar panels may move. We want to prevent the solar panels moving because that will cause the electrical cables that connect them, and some of them run at 600 volt DC to break and cause arcing and ignite the roof. This is a hazard, collapse, and possible fire that we need to be very aware of. Go to the next one, please. This is a ground-mounted large solar power plant. This is a ground-mounted large solar power plant. This is rated at probably about 300 and 350 megawatt, and this plant can run after sunset for a couple of hours. I will get into that a little later. These are called solar troughs. This has got a parabolic shape. This is a parabola, actually. It's a metallic, relatively light, and has got a reflective coating on the surface. Being a parabola, the hot oil line, this is the heat transfer oil, is located right at the focal point of the parabola so that it can concentrate all the solar energy onto the oil. These troughs are supported by the space frame, and also they rotate around this fulcrum to follow the sun. Here is the trough position at noon, they are facing vertically up with the hot oil lines running in the middle. Here is the hot oil line. And then they are in series and parallel to make sure the hot oil temperature increases as much as possible to somewhere around 700 degrees Fahrenheit. Go to the next slide, please. So this is a schematic arrangement of the hot oil system and the thermal power plant. It's a thermal power plant. Instead of burning coal, we are using hot oil. So the cold oil is going into the trough, becoming heated to 700 degrees Fahrenheit. Part of the hot oil going into the superheater, part of the oil is going to the reheater between the HP and IP, and rest of the hot oil is cascading down through the vaporizer, feed water economizer, and then the cold oil is coming out, and this is the pump which is putting it back into the field to be heated. And that's how the plant produces electricity. Remember, I told you that this plant can run after sunset for about 4 to 6 hours because of this system. Here, the hot oil, instead of going to the turbine and boiler, is heating up molten salt. This is a mixture of sodium nitrate and potassium nitrate and heated up to 700 degrees Fahrenheit. At the end of the day, the hot oil tank is full of molten salt at 700 degrees Fahrenheit, and the cold salt tank is empty. So when the sun sets, you pump the hot oil into a steam generator, take the steam and drive the turbine, same turbine, and put the cold oil back in, cold salt back into the cold salt tank. Very simple system. There's one problem. The salt can be heated to 700 degrees Fahrenheit. Sodium nitrate and potassium nitrate, they don't decompose at that kind of temperature. However, the cold salt freezes at 400 degrees Fahrenheit. Once it freezes, it chokes up the pipes, the pumps, and everything else. So they are very scared of getting into a 400 degree Fahrenheit or less temperature. So we recommended that they should have a contingency plan and a backup gas-fired oil heater in this, a salt heater, I mean, in this place, so that they don't have to go into a freezing condition. Once it freezes, it takes the plant to refreeze about 2-3 months of heating of this system, and that's a different problem. Okay, go to the next slide, please. Okay, before I go to this slide, let us go back to the last slide. How am I doing on time, Kamalako? So in this slide,
You have actually, we are running out of little time. Please wrap it up if possible in the next 5 to 10 minutes.
5 to 10. Okay, I'll give myself 10 minutes because I have about that much. So this plant have to be started every morning. So imagine that when the plant is being started, the water system in these heat exchangers are all stationary and cold. However, they have to start this pump and start heating up the oil, which slowly rises in temperature, 2, 3, 400 degrees Fahrenheit. And there is a huge temperature differential between the hot oil side and the cold water side. And that, now go to the next slide. Go to the next slide. The hot oil is running through the tubes and it is getting heated, but the water is stationary. So the delta T here is very high, causing enormous compressive stress on the tube plates, and they crack. Actually, in this particular plant, they cracked every heater in the plant because they did not understand this phenomena. So we had to redesign the operating logic of the plant to take care of the temperature differential must be maintained within design limits of the heat exchangers, and it was done. And these troughs and space frame that I showed before, they have failed severely at a local windstorm of 45 miles per hour. And in this particular area, the design wind speed should be 90 miles per hour. They reassured us they have designed it to 90 miles per hour, but it failed at 45. Basically, what they did, they took a lot of relaxation in the factor of safety and screwed up their design. So our recommendation in the standard is it has to be tested in a wind tunnel. That's what the genesis of that recommendation is. Go to the next slide, please. Okay, I have talked about all this. This is just for your information, freezing temperature and all that. I don't have to go through this slide. Go to the next slide, please. Okay, this is another newfound technology in our arsenal of fighting atmospheric heating. So the wind turbine. The wind turbine is very bad at controlling speed simply because we cannot control the wind velocity like we can do quantity of steam and pressure of steam, etc. So to control the speed, what they do, they change the pitch of the blades. And when you want to stop the machine, you turn the pitch to 0 and apply a brake on the high-speed shaft of the rotor, and that holds the blades in place. So from the control room, if you want to start the machine, you have to start increasing the pitch slowly so that it starts speeding up and release the brake. Now, there is a speed increasing gearbox which needs lubricating oil, and there is a nacelle which is made out of plastic, the whole enclosure, that's what you see, and there is the generator which also needs lubricating oil for its bearings, and this is the yaw control. It takes the signal from the wind vane and lines up the windmill with the airflow. But all this lube oil, this is cooled by a draft of air blowing through the nacelle. There is no cooling water system, nothing. So when the oil catches fire, there is nothing to extinguish it, and you will see in YouTube multiple postings of the windmill burning down to the ground. And this is the reason there is no fire protection here. Also, spacing of the wind turbine is very important because the blades accumulate ice and snow and all that kind of steel in cold countries and throw that. And once your control room is hit with that repeatedly, it can cause a lot of damage. The transformer and the electrical equipment are at the bottom of the tower. There is a door to open there and go inside the tower and climb up a ladder to the nacelle, which could be 50, 60 to 100 feet high. It cannot be located in a flood-prone area where the water can enter the bottom of the tower and flood all the electrical equipment. These are the hazards of wind turbines, and also the pitch control and brake operation is done from control room, so you should have a backup system. Otherwise, if the control room burns, you have to control each windmill from the base of its tower, and for 200 windmills, that's a hard task. Go to the next slide, please. This is my last slide. This is a gantry crane. These are used in industry all over the place, and this one is a small crane. I found this picture to show what I wanted to share with you. These gantry cranes are mounted on wheels here and run on tracks to and fro. Every wheel is driven by an electric motor, and all the motor shaft there is a brake. The brake is spring applied and solenoid released. So every time the operator wants to move the crane, he puts power to the motor. What the electricity does is first release the brake, then it goes. But these brakes are designed to hold the crane at only 30 miles per hour or so in service wind speed, because the manufacturer does not know where this crane is going to be installed. And they are quite often installed in ports and in other high wind areas. And the high wind have the effect of overcoming the brake resisting torque and push the crane down the tracks, and at the end of the track it hits a stop and topples into the water. We have got multiple losses of this type of cranes. So what the user have to do is to calculate the local windstorm velocity, the pressure on this structure, the force, and from that they can calculate the force along the length of the track and provide the securement. It can against the wind speed. It can be tethering, it can be rail clamps, and it can be stakes, etc. And those are all spelled out, how to calculate them, how to install them, are spelled out in this data sheet. Okay, go to the last slide, please. Okay, What I have given you is a very small window into the FM Global world. There is a lot more happening. FM Global does modeling of hurricanes, rainstorms, floods all over the world. You know, some countries like China and all, they don't have flood maps. So we have a model to predict that. I have highlighted some of the easily missed hazards in each subject to show you how easy it is to make a mistake. I have not discussed details or specific standards here. These are excluded. Over my 50 years of career, these are the golden rules that I have always followed. First is, and the golden one is, we never know everything, no matter who you are. You can be the chief engineer of the company. That does not mean you know everything. Engineering should be a collaborative effort. I should respect all colleagues, both above and below me, because one day somebody may point out a mistake to me and save my career. That's all I wanted to present. Thank you.
Thank you, Shyam. I really appreciate that. You tried your best to summarize your 30 years of experience in 30 minutes. It was a Herculean task. You did reasonably well. And I'm opening the floor for questions, but I would definitely, for my personal preference, I will ask Ochyuta to open it because he is familiar with many of the stuff you talked about. Ochyuta, please start.
Thank you. Thank you. I have one first comment. That is, the name of the lecture is very misleading. Why misleading? Okay, I'll come. You see, standard is in various fields in your life. There is a standard in potato, there is a standard in light, there is a standard in maps, there is a standard in pencil, there is a standard in pen. So the generalized statement of exciting world and developing and utilizing standards in real world and applications, that is a little bit misnomer. It should be more appropriate, a name should be more appropriate to the statements that Sri Shyam Ganguli depicted on his slides. But I do appreciate specific statements in very specific core areas, his depth of knowledge and the work that is being done for standardization of those products, and this effort is given free to all the people in the world to utilize in their own life, in their own work. So I thank first.
Thank you, Achyut. Yeah, I take your point, and I really, of course, in a lifetime, you cannot deal with all the standards. But let me make one thing clear. The name of the presentation is all Kamalakhu's fault because he is the one who suggested it, and I liked it and put it in. So, please take your gloves out and have a fight with him. I
And there is no fight. I surrender.
Thank you for your input. I really appreciate it.
Any other question, comment, suggestion?
I have put everybody to sleep.
No, that was very interesting. Very interesting. Very
That's not correct. That's not correct. It was a fantastic presentation, I tell you. Because we are all theoretical engineers, it is all new to me. But I enjoyed your presentation. Very nice.
Thank
you. It was indeed an excellent presentation, I must say.
Before I it to myself, I'm asking anybody else, particularly I'm asking the students, if there's any questions or comments.
It can be anything. Don't feel shy.
Yes.
I always have a standard answer when I don't know the answer. I don't know. I'll find out. So feel free.
Sir, in Kolkata nowadays, in Bodabajar area or in many old buildings, it is catching fire regularly. In frequent news, it is coming that it is catching fire. So, what are the basic causes and what the things the city should do or administration should do? Anything?
Being with FM Global for 31 years, we are totally sold on sprinkler protection, adequately designed and installed. So that will be my recommendation, because we know that when we go into a building, right, you can never find a source of ignition. If you found a source of ignition, don't call the engineer, call the fire department, because the fire is ready to begin. Okay. So the only way we can protect building is by designing and installing a proper fire protection system per FM global standards. Even NFPA will do. I have some disagreements with NFPA, will do. And those protection criteria are spelled in datasheet 3-26, and which I quoted in my presentation, and it is available to you from the FM Global website. Download it and take a look at it. And I'm telling you, fires will be there, but the objective of the protection system is to reduce the intensity of the fire to such an extent that it becomes a non-event. Instead of a building burning up, there will be one sprinkler head operating in one room extinguishing the fire. So that will save lives, that will save property, that will save everything. And this is what we have been selling for 187 years in FM Global, and we have been very successful.
I can add to this one, Shyam, that is in my country, there are people with bent of mind. They start the fire maybe intentionally in some of the cases for insurance and all that.
Okay, an intentional fire is what we call an arson. No fire protection, an arsonist always ignite the fire in 2-3 different places. There is no fire protection system that is hydraulically enough to extinguish a fire involving 3 fires in 3 different places in the same building. It does not work. So arson, we cannot protect.
Thank you.
You have a question? Yeah, go ahead, Pradeep. Unmute yourself. Unmute yourself.
I am unmute. Oh.
Go ahead. Now we can hear you. No, you are muted.
Hello, can you hear me now?
Yes, yes.
This is I'm of course Sam and Kamal's classmate, batch of 68. One thing I really I agree with Sam, because I've been in the nuclear industry for 45 years or so, and I know that there has been a lot of improvement and advances in the CFD area, and we have friends who are experts in CFD. But
What is
it is
CFD
true.
now? What is CFD?
CFD is computational fluid dynamics.
Yes,
or
yes, yes.
computational fluid and heat transfer
Yes.
dynamics. And of course, with the computers getting bigger and bigger and more powerful, the CFD is trying to solve many things. But I agree with Sam, and we had the same thing in the nuclear industry, that you cannot, ultimately you have to do large scale testing and see whether your theoretical model or computational model can actually predict that. So I agree with Sam that just because some expert in CFD says that I know what this fire is doing and all that, that is not true. Ultimately, you have to have a large scale testing. So that's my 2 cents worth.
Okay, guys.
Sam, it was a great presentation.
Pradeep is the most brilliant guy I know. He was our first boy. When he started asking question, I was very scared, but he let me off the hook quite easily. Thank you, Pradeep. I really appreciate it.
I have an addition to this. There are 443 power plants today in the world. Not all are working. Now, I have a statement all should be banished. No new power plant should be made in the world since I have got a reason. These are all man made products. All man made products, whatever kind of precaution you take, is going to have some accident someday or other. This
There
443
is nothing zero risk. It is impossible to
this
have
risk,
zero risk.
kindly permit me, then
Achyuta,
you have your say. Yes, please. Do I stop?
I have a, I
Yes.
have,
Kamal,
I have a comment to make along the line. Actually, Pradeep will talk about nuclear power pretty soon in the next 2 to 3 weeks. And
We will.
along Shyam's line, let me first tell you, the two persons we are always scared of in our lifetime in B college, one was Pradeep Shah, other is what? Ashok Malik. Ashok Da and Pradeep is
Yeah.
scary guy. Okay? And but that's a
Kamal,
different
Keep my
topic.
comment
Kamal,
Pradeep,
Kamal.
where are you now?
for that lecture.
Pradeep's
Let,
face I
let
am
me go
seeing
back
after
to
50 years. Where are you now?
Kamal,
Again, Ashok,
Pradeep, where are you
Where
now?
am I?
Yes.
Oh, I am in Raleigh, North Carolina, USA. Actually, I was invited to
Okay.
IIT Kanpur once by you
I
to
know.
give a lecture
Yes.
on nuclear computation and things like that.
That is the last time I met you.
Yeah, that must be late 80s or early 90s
Yes.
because
Okay,
I
thank
was in India from 85 to 2002.
You had a
okay.
company here. At that
Let's
time, you had a company here. When
I
you
had
came
a
back,
company, but again, this is not.
we'll talk about that next time. Coming
Yeah.
back to Uchita's comment
Yeah.
and basically
Kamal,
following what Pradeep
Kamal, I
said,
have a
I will agree
comment.
with that. Uchita, of course, I 99.9 times I agree with you, but this one time I will have to disagree with, due apologies, I will disagree with you because there is no such thing as Pradeep said, zero risk. If that is the case, probably we should ban all the cars. Okay? So that's not the right approach. Question is that
planes.
what Shyam is telling, what we are telling is that develop for the better. Okay? Learn from the mistakes. Okay? That's the engineer job. So, and Pradeep will talk about the nuclear power later, but yes,
Kamal,
that's why the standards are there.
Kamal, I have a
Coming
comment.
back to again his topic, I'm assuming there is no other question or comment. I'm making one quick comment.
I might mention one point.
Go ahead.
just
Go
one
ahead.
Yes, sir.
little point in a
Sure.
lighter vein. Achyuta, living is very risky. We should not stop living.
No,
Go
no,
on.
no. There is
Wonderful.
always a
We,
risk,
Kamal,
yes,
can
we,
you, Kamal, can you,
risk,
Kamal, I
balance
have a
yeah,
factor.
comment.
yes.
Risk balance factor.
Thank you,
In
Ashoka. We
various
should not be Nandolal, right?
Kamal,
great,
Kamal,
be happy. Be
Kamal,
present
I
in
have
this.
one
Andrew has a
quick thing to
question.
add. I have
coming
one quick thing
coming
to
back
add.
to seriousness of the topic, here's a question for you, Shyam. If we go back 9/11, I saw myself. Basically, I had a heart surgery at that time, so I was literally bedridden. I was watching in my living room, the Twin Tower literally fell, okay, one after the other. I saw literally second by second unfolding in my eyes. I couldn't believe it. The question to you from standard point of view, standardization point of view, have you seen or done or you know anything about where a fire starts from a snowball or fireball like a jet, which hits the huge tire and then what are the things, of course, we cannot stop it. As you said, it's something like arson. But question is that a lot of analysis has been done. If something happens, say on 100th floor of a 120-story building, and how we can save more life. We lost more than 3,000 people in 9/11.
Correct.
From your perspective, do you have any suggestion in future if somebody wants to do something similar based on your experience?
Before I start answering the question, I want to give you a little bit of background. We studied the World Trade Centers and the fire to the nth degree. we analyzed everything. The plane was full of jet fuel and it hit the building and the building collapsed. But before that, the structure of the building was such that there is a steel framework at the center core of the building. Okay. And that's where the elevators, the stairs, and all those were located. And as you come out of the elevator, their objective was to have a clear vision all the way to the window without any columns obstructing their view in the open spaces from the center core to the wall. And those were tied by steel beams from the center core to the wall structure. And entire load was carried by the central steel core. Now, as you know, steel becomes rubber. If it is heated to 2000 degree Fahrenheit, within 10 minutes, it will become rubber and collapse. Wood is better than steel in that respect. Okay. But of course, we cannot do a wood building that high. We have to protect the steel with insulation, fireproofing, so that it can last for 1 hour when exposed to 2000 degree Fahrenheit, not 10 minutes, right? The problem with fireproofing is it is physically applied to the steel structure, and there are what we call holidays. In other words, in some spots of the steel, the fireproofing is missing from abrasion, from heating, from work or something. We did research in our large burn laboratory, and we found that if you have a holiday size of a credit card, that column will collapse. Now compare that scenario with 500 tons of aviation gasoline pouring down the steel structure. Nothing can protect against that. So you have to go back to the structure of the building in such a way that you should not concentrate all the steel. Muhammad Atta was an architect. He understood the structure of the building better than most anybody. He was an engineer, an architect. So, but they even did not expect the spectacular collapse that happened. They thought there will be some collapse. Okay. Now, next to the Twin Tower, there was building number 7. The building number 7 was not hit by a plane and it collapsed. You know why? Because it was a telephone hotel. And every telephone system had a diesel generator so that they do not go out of the air with loss of electricity. They had their own generator, but they had a unique system. Every day tank of the diesel generator was filled up by a pumping system that pumped the diesel fuel to the top of the building and circulated it back to the bottom. And the diesel tanks tapped off their makeup fuel oil lines from there and controlled by floats in the tank. So what happened when that line failed, the pump down below kept pumping the diesel fuel. The line failed at the 6 or 7, this thing or something else failed. I can't remember now. And the fuel oil was pumped into the fire. No sprinkler protection, no fireproofing can protect against that fire, and the building 7 collapsed. So we know what went wrong. We do not know how to design a building against this kind of scenarios. We can cut down the effect of the fire to a certain extent, but can we prevent total collapse all the time? I doubt it. Does that answer your question?
Very well said. And
Beautiful,
this is
beautiful
the
answer.
reason I asked it, because the students who are here, they will understand the challenges of engineering field. Something like 200 story building, now we are making almost all over the world, and what we can do, what are the things we can avoid. So this is a very interesting insight into the problem. That is the reason I asked you, and you are absolutely right. This problem has been studied by numerous companies. numerous universities, it's all over the place, but this is good piece of information for the students who are here. Thank you, Shyam, for sharing with.
I just want to add one more point here. We in FM Global, we went to insure the World Trade Center a couple of times. We looked around and ran away from there. That's because we could not calculate how much it will cost to remove the debris and rebuild the tower in the event of a total collapse. That has never been done in a big city. And Lloyd's of London, they insured them for $1 billion, above $1 billion. Guess how much they lost? $1
Sure.
billion. And you know what our loss was because we ran away? We lost an adjacent hotel for $300 million. We wrote the check and we went home.
Okay. Actually, this raises another interesting point. This is mostly for the students. One of the things we learn and teach really all about engineering calculation, what can be done, what cannot be done, etc., etc. But we rarely equate engineering solutions, engineering designs with equity or dollar sign, as we call it. This is very important for our students to understand that it is not about just doing something design, doing as a team. More important that at the end of the day, customer, who will pay for it? Is it worth? That's very, very important. And this is exactly I liked when I started talking to Sam about 5 years back. His relationship, engineering and dollar. He's working for a company. They make money doing engineering analysis. They make tons of money, billions of dollars. So you need to think about always whenever you do something, in engineering calculation, who is their customer, how much they will pay, and whether there is any profitability. Think of the typical insurance as Sam alluded, it is mostly on actuarial. Basically, it means what the statistics says, what the probability that it will fail, and then they spread the risk equally for all the customers. Okay, there's no engineering involved. It's mostly statistics, most math, actuarial really. Where is what I'm
Kamal,
spending
kindly,
life? How equate engineering with dollar? Yes, Achyuta.
Kamal, one small point I'd like to mention. You see, in our design, we stop at some point. Let me explain. See, the seismic, you do a building for 7 seismic, 8 seismic, but you cannot design a building for 9 or 10 seismic. The cost will be enormous. The building will not be made. So we accept and we call it act of God. That kind of thing with atomic power plant also, I'll come on that day. You see, we accept certain things that this is beyond our control. These things will happen in the world as we live. These things we have to accept the risk. This is the risk. This is the cost. Beyond this, we cannot go. I have spoken enough. Thank you. Thank you for
Thank
permitting.
you. Thank you, Achyuta. So Pradeep, you know what is coming, right?
I know.
Actually,
Now, it is good that Sam gave the
actually,
lecture.
actually, it is not fair.
Chanda,
Achyuta,
Chanda
you give me
Kamal,
some hint. It might be now a common question. You will study, and Pradeep knows how to study,
Yeah,
so he will give the answer.
actually,
But
It's
it
better.
is
It's
great
better. We get a
that
good,
my
good,
presentation will
good
be 2
lecture.
weeks from now. I have learned from Sam now, what to say and what not to say and how to prepare my presentation because I'm in the middle of preparing it.
okay,
Good.
actually,
Pradeep, I dry
Achyuta,
run with Kamalakko. I did a dry run with Kamalakko. And I asked him, am I getting my points across? And he helped me a lot.
Lovely. You did it lovely, beautifully. The points are beautifully put. It's a very nice
Achyuta,
way of talking. Have I?
Achyuta, you know it
Have I?
again. Whom to blame if something goes wrong? Nando Ghosh is sitting here,
We have
but
got.
that's
We have got.
actually seriously speaking, Achyuta, you are right. This is, you cannot make anything foolproof. Fools
Yes.
are indigenous. So what we can do, cost of doing business. We know something, there is a cost. Okay. Is there any other question? I think we are getting carried away. It's a lot of interesting discussion. Is there any question or comment?
one small point I could mention. I mean, Shamda was showing a couple of slides on wind machines, wind turbines. In fact, only about a week back, or perhaps 10 days back, there was an event in Texas itself. So, lightning struck wind turbines, and there was a fire spiraling out of the turbine. So that was a catastrophic event, and nobody thought of it. So in fact, wind machines are considered to be somewhat immune to fire because it's really quite away from normal sources of fire. But it contains quite a lot of oil in its, even on top of the machines also. And they are also, mounted on high mast. So is there any fire protection, I mean, any initial thought on fire protection of this kind to arrest lightning? I mean,
Is
we
that
put lightning
Shubhendu?
arresters on top of buildings. Is there any such talk now that lightning has also struck wind machines in series?
Shubhendu,
Yeah.
you see the wind turbine, the lube oil system has to be cooled. The generator has to be cooled all inside the nacelle.
Yes,
And the
yes.
cooling is done with a draft of air tapped off from the front of the wind turbine, and it blows through the nacelle and exits at the end. So there's a huge flow of air there. And in that kind of flow, no fire protection system can operate successfully. It's very, very hard. Up until 5 years ago, we had no fire protection system there. Of course, you have to put, lightning protection, and keep in mind FRP, fiber reinforced plastic is also combustible. The blades are combustible, the nacelle is combustible, made of plastic, and the lube oil can fire. But the draft of air is what causes the problem. So when I retired, we had no fire protection system. Right now, 5 years later, I don't know whether somebody has come up with a solution. I doubt it. But I did hear that Norway or Denmark came up with a fire protection system. I have not seen it. I have not tested it. I have no idea. I only saying that I heard somebody did something. The Norway and Denmark and all these countries are significantly ahead of US in wind turbine technology.
Yeah,
So
but
they
most
have
of their
come up.
installations are offshore.
Huh?
Most of their installations are offshore usually.
Yeah, but offshore turbines have the same problem.
Offshore and onshore. Offshore and onshore. When you
Onshore
go to the
also,
ports,
yes.
in those countries, everywhere you will find wind turbine.
Yes,
Maybe
that's
in
why.
the machine itself, it's difficult to do something. But probably when we arrange machines in series, in between, perhaps we might to go for separate lightning arresters so that the machines could be.
Every machine should have their own lightning arrestor, and the space separation of the machine is very important for a couple of different perspectives. One is the shadowing of the wind. If you have two
Yes.
windmills, one right behind the other, the windmill behind does not get as much airflow as the first machine does. So you have to stagger them, and you have to space them. The fire protection system in the nacelle has not been, even water mist systems won't work there under that kind of airflow. So I am not aware of any protection system that is available by the time I retired and I worked on the standard. I don't know now whether something has been developed, but I doubt it. I don't see how we can do it except making it as fire resistive construction as possible, but you cannot get rid of the electrical system and the lube oil system and the draft of wind, because up there you want the nacelle to be as light as possible. So nobody wants to put a big CO2 cylinder or FM 200 cylinder or a water system or a mist system. That increases the cantilever effect of the windmill, and the windmill does this, and that's a problem. So it's a complex problem. Can it be solved? I think so. Has it been solved? I don't think so.
Thank you.
Thank you.
Any more queries?
You hear me? Come on.
Vidyut, you
If
can
not,
take over now. I think we are at the end of the day. So if
yes.
there's a question, Vidyut, you can take care.
Then Commander, let me have another couple of minutes just for Thanksgiving.
Sir, someone was asking something.
Students, yes.
Not student, Mr. Subhendu Dasgupta and some other.
Yes.
Come on.
You are asking something.
Yes. Who is there?
Kamal, can you hear me? This is Shovendu.
Yeah.
Okay.
Yes,
I was going to make a comment, and
sure.
I was not getting the opportunity. Now I got it. I can make that comment. Sham's. Uh, so I know what Sham's working field was, and it was a great presentation, Sham. I really appreciate that, and it's very informative. One thing that I just want to add, because I have worked in nuclear power all my life here in the United States, so I only know nuclear. And on the nuclear power, the uh, insurance is completely different entity. Is ANI, and they
Yeah.
have totally different standard to deal with,
Sure.
and they are more stringent in terms of implementing the standards. Like when we had the Fukushima Daiichi issues, those new design standard that came out of that incident had to be implemented in the United States, and every single nuclear plant within the time frame of almost like 3 years or 4 years. So all 110 nuclear plants have been upgraded to Fukushima, and the insurance company was part of that whole process. There were some issues on the standards on the nuclear, and mostly like torsional failure of the turbine. It's a big deal on the nuclear, and I don't think FM Global get involved into the nuclear side of the business. Am I correct, Sam?
No, we stay out of the nuclear power plant on the reactor side, because for that you need more qualified engineers
Yeah,
in the nuclear industry, which I am not. But we provide ASME code services to nuclear power plants. Like, we had 4 engineers at San Onofre generating station, but they
yeah,
only did the ASME code work. They did not get into reactor
yeah,
code and nothing like that. I
yeah.
am very familiar with what happened at Fukushima Daiichi, 3 Mile Island, and all that. But we are willing to ensure only the steam turbine cycle in a nuclear power plant. But normally, nobody wants to separate the reactor from the steam turbine cycle. Oh my God, we don't know reactors. We are not going there. And also, FM Global is deadly scared of paying for nuclear pollution in the event of something going wrong.
Yeah,
$20 billion would be nothing.
yeah,
So we stay out of something that we don't know how to handle.
yeah. Thank you.
Yeah.
That was my small questions, a small comment.
Thank you,
for Sam.
Shubhendu. It was a very interesting question, and and probably will something will come up hopefully later. But Shyam, this came to the same point again. I was trying to tell you. Basically, this is a balance between engineering and economics. Okay, FM Global decided it is beyond the engineering means of today's technology, so they're not touching it. Okay, it makes sense. It is their business. Is there any other question or comment or suggestion? If not, Pradeep, you can do your,
Yes,
Bidut, you can
Commander,
do
yes.
last rituals. Thank you
Yes.
so much. Thank you, Sam. I really appreciate it for coming.
On,
Thank you, everybody. Thank you, Achyuta, Ashokda, everybody.
I
Okay.
thank
Bidut,
Kamal for
Sudeep, you
handling
take
it
over.
beautifully.
and on behalf of the department and the Centenary Celebration Committee, let me thank Mr. Shyam Ganguli for today's presentation. Wonderful talk on standards and making of standards. It was indeed interesting. I must also thank Professor Kamal Sarkar for chairing the session so nicely. One last responsibility is, as a token of appreciation, we have this soft copy of the certificate, which we will be sending to our speaker through email, and a hard copy of this along with a memento. We will keep ready here. We will try to hand over to whenever Shyamda happens to be around in Calcutta, or maybe we will arrange to send it to Shyamda via
Thank you.
somebody.
I'll frame it up and I'll show it to my sons. They don't believe I'm educated.
Thank
Lovely,
you,
lovely.
Shyamda. Thank you, Kamalda. And thank you all other senior members of alumni for joining today's session. Thank you. So we'll close the